So there's three documents we're going to be focusing on this morning. One is the slides. These are available as a PDF file in the Day 5 Inference folder called Day 5 Slides. So I will be going through those. At some points, I will flip over to the HTML file from the Quarto document that says Day 5 PM Lab, where we're going to use the beginning part of this to have some examples for each of the concepts that we're going to talk about today. And then also you can open up the .qmd file itself in R, which this will be helpful when we want to run some of this code or we want to manipulate it and do some possibly do some different things with some of the variables we're going to be looking at. But we're going to start with we'll start with the slides here today. So far we've been talking about R strictly, how to read in data, how to manipulate data, how to plot data. We haven't really talked about any statistics quite yet, so that's what we're going to start talking about today is statistics and statistical inference. We're going to start from a pretty low level, talking about probability. Then we'll work our way up to distributions, and we'll do some hypothesis tests and confidence intervals towards the end of today, and that's what you'll work on in the lab portion. So the start with probability here. I'm just realizing I'm missing some markers. Anyone have any dry erase markers on them? No. Okay, I think I can probably make do without. Yes. Okay, awesome. Thank you. I'll get some more during the break, but I will be writing on this board a little bit. I'll try to make it big enough for everybody in the on the online to look at, and I'm not going to use it too much. But we'll start very basic with probability as a number between 0 and 1, where probability of 0 means an event cannot happen. Thank you very much. Wow, orange. Good. Probability of 1 means an event will certainly happen. Useful way to think about it, we repeat an event many times. How many times would we see this event occur? If 10% of the population carries a particular gene variant, then a randomly selected individual, the probability would be 0.1. There's some rules we use in probability, which end up being helpful for various things. Particularly when we're talking about the probability of two events. Finding the probability of one event, okay, we can do that. But finding the probability of two events can be a little bit harder. There's two ways we can be interested in this. The probability of both events happening, their intersection, or we could be interested in their union, probability of either event happening, A or B. When we want to calculate the probability of A or B, we can see the formula for that right here. Probability of A plus probability of B minus the probability of A and B. So an easy way to think about this is through a Venn diagram, for example, where we have two events A and B, where the size of the circle here is roughly the probability that A would happen, size of the circle probably B would happen, and then we have this little part in the middle where they both happen. So if we want to calculate the probability either one happens, we want to calculate the probability of this outline here. And if we just add A and B together, we calculate this middle portion twice. So for example, if you have two events and both have probability 1/2, and let's say, for example, the probability of what's happening in the middle is 1/4. This is something that often gets confused. The probability of A or B would be 1/2 plus, actually, let's say the probability is 1/4. And I'll tell you why I like to look at this one. Probability is 1/4 for the first event, 1/4 for the second event, minus 1/16 for the intersection. And if we calculate that all together, 8/16, this is 7/16, 0.4375. When does this probability come up? Well, when I see it come up, has anyone ever heard of Texas Hold'em? No, I'm fine. Anyone ever heard of Texas Hold'em poker? Okay, so Texas Hold'em is this game where you have two cards in your hand, and they put some cards on the table, and anyone can use those cards. And they initially put out 3, and then they'll put out 2 more. So when does this probability come up? Well, it comes up when between what you have on the table and what you have in your hand, you have 4 of a particular suit. So let's say you have 2 hearts in your hand and there are 2 hearts on the table. Now, to get a flush, which is a very good hand in poker, you need either the 4th card or the 5th card to be a heart. Now, there's 4 suits, so the probability of seeing a heart is roughly 1 out of 4 in the first for the 4th card, 1 out of 4 for the 5th card. So a lot of people think, well, there's a 50% chance I'm going to get a flush. It's not the case. Because you have to take away the intersection of the 2 events, probability is closer to 43, 44%. So that's why you won't see professional poker players put a lot of money on a hand like that, because the probability they win the hand is less than 50%. And in the long run, that's not going to be a good bet, right? So that's one place I always see that probability, this union come out to be something different than most people think it is. Complement of events, these can certainly be helpful. Example here, if we have 47% of the respondents are male, 50% are aged 18 to 44, with 27 being that intersection, the probability that you're male or age 18 to 44, 0.47 plus 0.5 minus that intersection, or 77%. I mean, you can tell that just adding the 2 would be wrong, because you would get 97%, and clearly that's not going to be right. Get my control on this. Yeah, good. Okay. Something that we do a lot in statistics is we deal with stuff called conditional probabilities. So conditional probability here is the probability that event A happens given event B happens. Comes up all the time in statistics. For example, what is the probability a patient tests positive for a disease given they are in the high risk group? Or what is the probability patient has a heart attack given they have systolic blood pressure greater than 200? We're very interested in conditional probabilities because they can be used to relate events to one another. For example, we can look at the probability that you get a heart attack given you have a blood pressure over 200 versus the probability of a heart attack given you have a blood pressure under 150, for example. We can compare those two. So conditional probabilities are very useful. Independence. This is something that occurs when 2 events are unrelated to one another. And we can see that when 2 events are independent, the probability of A given B is the same thing as the probability of A. For example, the probability I go to Chick-fil-A for lunch today, given the Mets lost last night. They're not related. Okay. It's not going to be anything. I'm not a Mets fan, and the Mets stink. They always lose. Okay. So these things are not going to be related. So when we talk about independence, we have events that are not going to be related to one another. So another nice property of independence is that when two events are independent, the probability of A and B is equal to the probability of A times the probability of B. So it makes calculating that intersection very simple because we just have to multiply the two probabilities together. Okay, and many genetic studies, we assume that two SNPs on different chromosomes are inherited independently. They don't have any relationship to one another. Yeah, so and one thing, pardon me if I use too many sports references today. So one thing I think is very interesting. So obviously, you guys all know I'm an NBA fan. And the way they do the NBA Finals, it's a 7-game series. You do 2 games at the one team has home court advantage. Okay, here Finals, Spurs have home court advantage. Knicks don't. So the first 2 games are in San Antonio. Second 2 games are in New York, and then they go San Antonio, New York, San Antonio. What bothers me is how people talk about the first 2 games and the outcome of the first 2 games. Okay, so who's more likely to win? Just in the overall, the home team or the away team? The home team's more likely to win. Okay, so the first 2 games are, they're in San Antonio. Say we don't know that New York won the first game. And what bothers me as a statistician, someone who knows probability, is how people assume that the home team is going to win the first 2 games and that that's the most likely outcome, that the home team is going to win the first 2 games. So let's say, for example, the probability Knicks win game 1, I'm just going to say KG1, is the same thing as the probability that the Knicks win game 2 is equal to 0.3. So there's not a good chance that they're going to win either home game. Only a 30% chance. That is very low. The probability is not going to be that low. When the teams are even, that probability probably about 45%. Home court doesn't matter all that much. So I'm saying home court really matters here. Now, what's the probability that the Knicks win game 1 or they win game 2? Okay, what's the probability that they win game 1 or game 2? And let's also say that these are independent. Okay, so the probability, I'm just going to call this one A here and call this one B. So the probability they win game 1 or game 2. So I'm saying, what is the probability that we don't see the home team win both games? Now, you would think probably the home team's going to win both games, right? The home teams are going to be big favorite, 70% chance they win game 1, 70% chance they win game 2. So what's the probability we don't see that? Well, we can just use what we had earlier, probability of A plus the probability of B minus the probability of A and B. And we can use the independence here. So this is going to be 0.3 plus 0.3 minus 0.3 squared. So this is going to be 60 minus 9, 0.51. So that means the probability that they win one, at least one, is over 50%. It's over a 50% chance, even when they are huge underdogs. Even when there's only a 30% chance that they win either game. It's what annoys me that everyone says, oh, home team should win the first 2 games. That's not the case. What should happen, what's most likely is going to happen, is that one team wins one team wins the other. That is the most likely case when you actually look at the probabilities, unless the home team is way better. They have to be have over a 70% chance of winning either game. Okay. That's my rant. It's related to this. It bugs me when people talk about that. So now at least I've told all you and all you online about it. Okay. Next thing we're going to talk about is random variables. We're interested in random variables. We're interested in outcomes. We're interested in exposures. These are random variables. We want to relate these to probabilities. To do that, the first thing we need to do is we need to figure out what type of random variable we have. And we have two types that we'll talk about: discrete random variables. These could be categorical. Okay, it could be disease, not disease, just 0 or 1. This could be disease, kind of disease. This could be like BMI category, where we have maybe 4 different categories. This could be a count, like how many skin cancer lesions you have on your body, 0, 1, 2, 3, 4, can keep going. Those are all discrete random variables. We also have continuous random variables, which can take on any value in a particular range. For example, body weight, blood pressure, gene expression level. The first thing about probabilities is we need to put it into one of these two categories. Some common statistics that we will calculate are mean and standard deviation. The mean, of course, this is the long run average, the center of mass of the distribution. Standard deviation is a measure of the spread around the mean. Large standard deviation, or large sigma, means the data are widely scattered. Small sigma, that means they're all pretty close to the mean. You can see the formulas down there for mean and standard deviation. And for example, we have 5 crab weights here. We can calculate the mean, 0.8 kilograms. We can calculate the standard deviation. Okay, we'll be using these as we move forward. The first distribution we're going to talk about is the binomial distribution. And there's actually a very interesting story about how the binomial distribution was initially invented by a famous statistician. Poisson was his name. But how this came up was Poisson and a friend and another woman were talking about T. This is in like 1920, 1910, around then. And the woman claimed that she could tell when someone had poured milk, because she liked her tea with milk. And she claimed that she could tell if the milk had been poured in the cup first, or if the tea had been poured in the cup first and then the milk went in. Okay? She claimed she could tell the difference of these. Like if you brought her a teacup, she could say, all right, milk went in first, tea went in first. It's insane, right? Like, I mean, I can't imagine that anyone could do this. And what they said was, okay, we're going to do this experiment. We're going to have 8 cups of tea, 4 where the milk was poured in first, 4 where the milk was poured in second. We're going to randomize the order, and we're going to bring them out, and we're going to see, hey, can you tell if which one was poured in first, which one was poured in second? So if she has no clue and she's just guessing, the probability she gets each one right is going to be 1/2, right? If she just flips a coin, or if she just guesses the same thing every time, the probability she gets them right is going to be 1/2. So there's going to be 8 trials. There's going to be a 1/2 probability on each trial that she gets one correct. Now, X is going to be the total number that she gets correct. Now, the most likely value is 4. She would get 4 right. She would get 4 wrong if she has no idea. But when do we say, wow, this lady actually can do this? Like, she can actually tell the difference. If she got 5 right, is that crazy? I mean, if the probability is 0.5, is 5 like a super weird value? Probably not. I mean, it's probably within in the range of within the realm of what's possible. 6, okay, starts to get a little weird. If she gets 7 right, okay, then you're like, wow, this really knows. If she gets all 8 right, and actually the probability that she would get all 8 right is 1 out of 70, even if it's 1/2. It's possible. It's possible. You can't get lucky. You can take a coin, you can flip it up, 8 times in a row. 1 out of 70 times, you'll get all heads or you get all tails. This is the binomial distribution. This is how the binomial distribution was invented. So the binomial distribution gives us those probabilities. Given there's 8 cups of tea and the probability is 1/2, what's the probability she gets 8 right, 7 right, 6 right, all the way down to 2 right and 1 right? This is the binomial distribution. So it gives us probabilities under a hypothetical scenario. The scenario is the probability of success is the same on each trials, and the trials are independent. Trial 1 is not related to trial 2, so on and so forth. And we see some other biological examples here where the binomial distribution comes up. All right, so now we're going to move over to our HTML file here. Make this a little bigger. So we're going to use R to access these distributions. For example, this binomial distribution that we have. When we use distributions in R, there's a number of different ways we could use them. And we have one, it will use the R followed by the distribution name, but the D followed by the distribution name, the P followed by the distribution name, or the Q followed by the distribution name. They all have these letters in front. It's going to be R, D, P, or Q. So let's go down to the binomial example, which is actually the second one on here. So let's say we have 20 patients, each with a 30% response probability. How many do we think are going to respond, and what's going to be the distribution of that variable? So this first line right here, the R, this is when we want to generate data from that particular distribution. And this ends up being useful for us to demonstrate statistical concepts like I'll use in here. It ends up being useful for us when we want to test statistical methods. So how we generate data, that's when we have the R in front. So if I want to generate data from a binomial distribution, I use R binom. The arguments are N. That is how many samples do you want to generate? The size, 20 here. So we want to have 20 replications. And the probability, which we have here, is 0.3. So here, I just simulated it once. I got the number 9. The second time, I simulated 10 of these. And you see the values that I got for those. So these are random numbers, okay? Random numbers simulated. Here is a bunch of random samples, 10,000 in fact. And this is what the distribution of the binomial distribution looks like when we have a size of 20 and a probability of 0.3. So we can see that the most common value here is 6, followed by 5, then 7, 4, so on and so forth. We can see some of the values that are very unlikely to happen. 0 is very unlikely to happen, and really anything above 12 is very unlikely to happen. Out of 10,000 times, out of the 10,000 simulated values, we just have a handful down at this component right here. So the R distribution name simulates random data. R binom, we're going to use R norm, R Poisson. Those are all going to simulate data. The next one is the D prefix. So D binomial. This will give me the exact probability that a particular situation will happen. So here I'm looking at same situation, size of 20, probability of 0.3. What is the probability we get exactly 8? The probability we get exactly 8 is about 11%. The P binomial is going to give me the probability that a value that we see greater or less than a particular number. So here we're doing 1 minus here. So what this is giving us, P binomial gives the probability, by default, it'll give us the probability that it's less than or equal to the particular value. So I'm saying here, what is the probability that we see 9 or fewer when the size is 20 and the probability is 0.3? Now 9 is going to be up here. So this is going to give me the probability of all this part down here, which is going to be pretty large. I'm taking 1 minus that. That gives me the probability of 10 or more, which is about 5%. So there's about a 5% chance that we see 10 or more values when we use this particular distribution. Q gives us the inverse of P. So you give Q a value, a quantile, for example, and it'll give you the value that corresponds to that. So really, mostly what we are going to use is the R to generate random data, the D to get exact probabilities, and then the P to get a value or less than that. Okay, and we use 1 minus to get greater than that. Those are the 3 main functions that we'll use these for. So for example, we can go back to that lady tasting tea example. What is the probability that she saw, say, so P binomial, what is the probability that she got more than 4 of the 8 trials if the true probability was 1/2? About a 36% chance. So the probability she got 5, 6, or 7, or 8 happened about 1 out of 3 times, even if the probability was 1/2. If she saw that probability of 6, 7, or 8, no, I did that wrong. That'd be 5, is about 1 out of 7. So if the true probability was 1/2, the probability she got 6 right, 7 right, or 8 right is about, it happened about 1 out of 7 times. And at that point, you're like, yeah, maybe this woman actually knows what she's doing. Yeah. So, yeah, good question. So if I want to know the probability that the woman, let's use D here. So the probability that that woman got 6 right plus the probability she got 7 right, exactly 7 right, that's what the D gives us, plus the probability she got 8 right. If I want to add all those 3 together, you see that we get 0.114, which is the same as we got here. This is going to be, this part right here is the probability that she got 5 or less. So when I do 1 minus the probability she got 5 or less, it's the probability she got 6 or more. Good question. We could do it either way. We can do it either way. And same thing on the bottom side. If we wanted to know what's the probability she got 0 right, or let's say 1 right, this would be if things went really bad. We see that it's equal to that. That'll be the same thing as this P binomial at 1. So P binomial 1 gives us the probability of the value or anything less. When we do 1 minus, we get probability it's greater than the value that we're giving. Any other questions? The next distribution is the Poisson distribution. And Poisson is one that we use for counts. So for example, the example I gave earlier, the number of skin cancers on a particular patient, that's a count. Can be 0, can be 1, can be 2. Number of mutations per kilobase in a genome, number of bacterial colonies on a plate, number of rare disease cases in a county per year. So this, when we have variables like this, we'll typically describe them through a what's called a Poisson distribution. And this leads to the Poisson regression, which is something we use when we have outcomes like that. And we also have this distribution available to us in R. Here, for example, we're using we're simulating 10,000 Poisson random variables with a lambda of 2. So that's going to have a mean of 2. It's also going to have a variance of 2. And we can see the histogram of what that looks like. Most likely value is actually 1, followed by 2, then 3, then 0, then 4, so on and so forth. We have D Poisson. This gives us the probability of exactly one particular value. So for example, the probability of a 0. P Poisson, this gives us the probability of the value we're putting in or less. So here, P Poisson of 4, comma, lambda 2, that would give us the probability of a 0, a 1, a 2, a 3, or a 4. When we do 1 minus that, gives us probability of a 5, a 6, a 7, 8, all the way up. We see there's a 5% chance of that happening. All right, now we come to the most popular distribution in statistics, and really probably the most popular distribution in nature, something called the normal distribution. The normal distribution was first developed by a mathematician named Frederick Gauss. So the normal distribution is sometimes called the Gaussian distribution after the person who invented it. How it came up is early 1800s, people would measure like the locations of stars. This is early 1800s, and they all had different telescopes, and like the telescopes had issues to them. And what they noticed was that the measurements would all be different. They'd all be slightly different. But if you looked at them in a histograph, they would have the famous bell curve to them. They would have like this nice bell curve. And what Gauss did, and he said, all right, what is the distribution that bell curve represents, such that the mean is the best guess of the middle? That's where we get the normal curve from. But this is the classic bell curve. It occurs a lot in nature. Another place that another time where this distribution came up, this was after Gauss, was a statistician when he started to look at the measurements of soldiers. This was in the later 1800s. So they had like chest measurements of all the soldiers, heights, weights of all the soldiers. And he noticed that when you plot these on a histogram, again, they have this like bell-shaped curve. And I can't remember the name of the statistician who did this, but he said, all right, this is obviously like God's curve. This is the curve that's driving human nature. And anyone that's outside this curve is against nature. It's like anti-nature. It's a mistake of nature when anyone comes up against this curve. So not a great, probably wouldn't fly today, but yeah, the normal distribution. There's so much of statistics that is governed by the normal distribution or the t-distribution. Okay, it pops up all the time. We'll see one reason why in in P slots. How we write this? We write the normal distribution in terms of the mean and the variance. The sigma squared, that's the variance. When we take the square root of that, we get something called the standard deviation. So sigma is called the standard deviation. Sigma squared is called the variance. For a normal distribution, about 68% of all data are going to be within one standard deviation. 95% of all data are going to be about 2 standard deviations away. Okay, so most everybody is going to be within 2 standard deviations of the mean. 2.5% on the right, 2.5% on the left, okay, are going to be within there. So if you're more than 2 standard deviations away, it's kind of like, wow, you're a good distance away. You either have a very high value or a very low value. 3 standard deviations away. So 99.7% of all data fall within 3 standard deviations away. Okay, 3 standard deviations of the mean. So we use this all the time. So adult blue crabs, let's say they the weights follow a normal distribution with a mean of 0.8, variance of 0.3 squared, standard deviation of 0.3. I want you to understand the difference between the variance and the standard deviation. Okay, so usually the way we write a normal distribution is we get the mean and the variance. Okay, but we don't really use the variance. We use the standard deviation. So that's why I write this as 0.3 squared. The variance is 0.3 squared, but from this, it's also obvious what the standard deviation is, which is just 0.3. Because standard deviation is what we use. Okay, 68% are within one standard deviation. They're not within one variance, within one standard deviation. Okay. And this one is also available in R. And this is the normal distribution. So when we want to generate from this, we have R norm. So one different thing about the normal distribution, this is a continuous distribution. Okay, these are continuous values. These are not discrete like the Poisson or like the binomial work. These are continuous values. So I'm generating 1,000 crab measurements with a mean of 0.8, standard deviation of 0.3. Then I'm calculating the mean, and we can see that I'm calculating how many of the crabs are greater than 1. And then I'm using the p norm, 1 minus the p norm, to get the probability that a crab is greater than 1, and we see that they're very close to one another. So about 25% of the crabs in the sample are greater than 1, and it should be about 25% if we use the p norm value. And here is just a histogram of those blue crab weights. I'm overlaying a normal distribution curve in red. So in red, that's the normal distribution curve when the mean is 0.8 and the standard deviation is 0.3. So we can see how the histogram looks compared to the true distribution. Theoretically, these things are should be equal. We see some random variation. Okay, it's just bouncing up and down. Some of these are above, some of these are below what we would expect. So here we're looking at the probability within 1, 2, and 3 standard deviations. Probability we are within 1, about 68%, within 2, about 95, within 3, about 99.7. So we are going to use the normal distribution all the time. It comes up so frequently. So adult blue crab weights, let's say it's the mean is 0.8, sigma is 0.3. What's the probability a randomly selected crab weighs more than 1 kilogram? So the first thing we would want to do is figure out how far is 1 kilogram from the mean in standard deviation units. How far is 1 kilogram from the mean in standard deviation units? So to do that, we calculate something called the z-score. And that is the value we're interested in, 0.1 minus 0.8, that's the true mean, divided by the standard deviation. So 1 kilogram from the mean in standard deviation units, 1 kilogram is in standard deviation units 0.67 from the mean. And then we could look this up in R, probability that a standard normal is larger than that value. We get 25%, which is what we got in the when we did this in R. Now, the reason why the normal distribution comes up is something called the central limit theorem. And this is why the normal distribution comes up so often in statistics, is the central limit theorem. What the central limit theorem says is that suppose we have some measurement on n individuals and we compute the sample mean, x bar. Now, it doesn't matter what distribution the data follow. It could follow a Poisson distribution, could follow the binomial distribution, whatever it is. It could follow any distribution. No matter what, the distribution of the mean is going to be normally distributed. The mean of that distribution is going to be equal to the mean. The variance is going to be equal to sigma squared over n, which is the sample size that we use to calculate the mean. As the sample size grows, as we get a larger and larger sample size for our mean, the variance gets smaller and smaller and smaller. So the bigger sample size we have, the closer we are going to be to the true mean, the less variance we are going to have. It becomes more precise. And the central limit theorem, as I said, this is the central reason why the normal distribution comes up so frequently in statistics that we see it a lot. So we have sigma squared over n. This is the variance of the sample mean. The standard error of the mean, SE, is going to be sigma over square root of n. And that is just the square root of sigma squared over n. That's called the standard error. And the standard error is going to tell us how variable our estimate of the mean is. So let's say that sigma was equal to 0.2. If we have 4 samples, the standard error of the mean is going to be 0.1. So if we have 4 samples, we expect the mean to be close to the true mean, to be within 1 unit of the true mean about 68% of the time. If we have 100 samples, the standard error is 0.2. So if we have 100 samples, the sample mean is going to be 0.2 units from the true mean about 68% of the time. So it's going to be pretty close when we get to that 100 samples, 100 sample value. Larger samples, more precise estimates of the mean. Okay, let's take a look at this in R. And this is where we can start using the simulated data to demonstrate some of this behavior.
What should the reproducibility of the experiment, standard error? Something like that.
So what we're going to do, so the sample size obviously is an important quantity to reproducibility. The larger sample size, the better you think your inferences are going to be. But there's a lot of design aspects that go into a study as well. How good is your sample? Is it a representative sample? Is it a random sample? That goes into reproducibility. If you don't have a random sample, the next person trying to do it, they may get a sample that's different, which may give different values. So it does point to the reproducibility, but there's also a lot of other issues that are going to play probably a bigger factor than this. So we are going to simulate, what do we have here? 10,000 variables from something called a exponential distribution. And this is a look at the exponential distribution. This is a look at the histogram of the exponential distribution. You can see that it is very skewed. Okay, this is definitely a right skewed distribution. The values, most of the values with the highest bars here are very low. They're in bins that, are less than 1 unit. But we also have quite a bit over 5 units and some that are even over 10. So very right skewed random variable. Does not represent a normal distribution at all, right? We can agree on that. It's very skewed. Doesn't have that bell-shaped curve. The next thing we are going to do is we are going to take a random sample from that exponential data, and we're going to calculate the mean. And then we're going to take another random sample, and we're going to calculate the mean. And another random sample, and we're going to calculate the mean. We're actually going to do this 5,000 times. Each time we're going to take it. We don't actually have to do it 5,000 times. Okay, I'm not going to have you like calculating this 5,000 times. R is going to do all this. We're going to do this 5,000 times in R, and we're going to look at what does the mean look like? What's the distribution of those means? We're going to do this for 3 different sample sizes. First, we're going to do a sample size of 5. So that means we're going to take a sample size of 5, calculate the mean, another sample size of 5, calculate the mean 5,000 times. Then we're going to do it for a sample size of 30, a little bit bigger. Then finally, we're going to do it for a sample size of 100. Okay, that's going to be the largest. R is going to do all of this for us, and then we're going to look at the distribution of those sample means. And that's what we see here. Okay, so on the left, this is how the means look when we have n equal to 5. So when we have n equal to 5, the distribution of the mean is still somewhat skewed. Okay, still somewhat skewed. Now, why is that? I just told you that the mean is always normally distributed. Well, it's when n is large, okay, that's a key component here. When n is large, the mean is going to be normally distributed. 5 is not large. This is a pretty small value. So it does not have a normal distribution when we take a sample size of 5. But even when we get a sample size of 30, even when we have that sample size of 30, it starts to resemble a normal distribution pretty closely. There's a little bit of skew in there, a little bit of tilt towards the right, but it's really not very large. And a normal distribution could fit that pretty well. And then when we're at 100, clearly we're looking at something that looks very, very normal at that point. So this is a demonstration of how the central limit theorem works. How big of a sample size do you need? It depends on what your original data looks like. So here we're dealing with a very right skewed data. And when we start from that, you can see we need to be at least at the 30 part before we really start seeing that central limit theorem. But if we have data that are more symmetrically distributed, for example, this Poisson data right here is a little more symmetric still. That one, the sample size we need is not as large. So the sample size gets bigger. It looks more and more like a normal distribution. Also, we can see the spread, the values that we get narrower and narrower. So this for the 5, we're getting values almost all the way up to, well, 5 definitely. We have a sample size of 5. We have some values that are greater than 5. When we have a sample size of 30, nothing greater than 5, nothing greater than 4. We have some that are greater than 3. When we have a sample size of 100, maybe like 2.5 or so is where those really large values we're getting. So we're getting narrower and narrower. We're getting better and better values. The true mean here is equal to 2. and we can see the 30 sample size and the 100 sample size. We are very close to that 2 value. The peak of that is. So 2 things we see: larger sample size, the shape becomes more and more bell, and 2, larger sample size, the spread of the distribution is getting narrower and narrower because sigma squared over square root of n is going to be shrinking. And we can calculate the standard errors here. The population standard deviation. Here's the standard error when we have n equal to 5. Here's the standard error when we have n equals to 30. Here's the standard error when we have n equals 100. And these match what we get very closely based on the data that we have. So we never observe, the whole population. Like in that example, we had all these exponential random variables. We never observe that. What we are going to observe is the sample. So if we have a sample of 100, that's what we're going to see. So this is just an example of what we can expect from the sample that we have. And we're going to use this to try to give us some information about what's going on in the population. So we know that when we have a sample of 100, the distribution is going to look like it does right there on the right. Okay, we know that. So later on, when we do have a sample of 100, we can use the fact that the distribution looks like that to tell us some information about what the true mean of this data is. And this leads us to confidence intervals and hypothesis tests that will go next. These are both built on the same foundation. Hypothesis test: is there evidence against a specific claim? Do we see evidence of that? Confidence intervals: what is the plausible range of the true value that we're interested in? So when we do hypothesis tests, the core idea is we start with a default claim of no effect or no difference. For example, this drug does not change blood pressure compared to placebo. We collect data. If the data were very unlikely under H0, we would have evidence against it. For example, in the lady tasting tea example, our initial assumption was that, okay, she doesn't know the difference between milk first or tea first, and then it's a binomial with probability 1/2. That's our initial assumption. We collect data, and then we can use that binomial distribution to say, all right, when does it get to a point where we're like, okay, something's wrong? And what's wrong likely is that the probability is actually not 1/2. So if she gets all 8 right, we would say, yeah, the probability wasn't 1/2. That's only going to happen 1 out of 70 times if the probability was 1/2. This is the basic idea of hypothesis testing. We start with the claim. Okay, the claim is that the null hypothesis there is that the probability she gets it right is 1/2. We take data, and then we look at, okay, how weird was this data given our initial claim? If it was really weird, then we say, all right, our initial claim was wrong. Something went wrong there, usually. So the p-value, that's the quantity we get for how unlikely this data were. So for the lady tasting tea, if she gets all 8 right, the p-value is 1/7. How unlikely was this to happen if the probability was truly 1/2? Well, 1 out of 70 times. If, like I was showing before, where is it? This one right here. So that's the probability she got 7 right or she got 8 right. Was about 3.5%. So if she got 7 right, we could say, all right, what is the probability she got 7 right or 8 right? If the probability was 1/2, well, it's really 3.5%. That would be our p-value. Okay, how unlikely was this? How unlikely was it that we saw what we saw or something worse. And that's where we get that 3.5% from the p-value. Okay, that's a good place to break. We'll come back here maybe a few minutes before 11:15, and we'll get to some hypothesis testing, actually completing some hypothesis testing and some confidence intervals, and we'll do some hypothesis tests. So we finished the morning talking, or not the morning, the first part of the morning talking about p-values. Continue with that here. We're going to use p-values in something called hypothesis testing. The first example we're going to go to, we're going to be looking at systolic blood pressure. Okay, so what we're going to look at, we're going to get the X bar of systolic blood pressure from the data. Okay, the X bar of systolic blood pressure from the data. And we know from the central limit theorem that this is going to have a mean equal to the true mean systolic blood pressure, and the variance of this statistic is going to be sigma squared over n, where sigma squared is the variance of systolic blood pressure in our data set. What we may be interested in is testing, is the systolic blood pressure equal to some value, right? So the healthy systolic blood pressure would be, say, 122. So we may be interested in testing, is the mean systolic blood pressure in our sample 122 units? So we will assume that it is 122 units, and then we'll see how weird is the sample mean that we got. So if the true mean is 122, then the sample mean, the distribution of it is going to have a normal distribution. In the center, we're going to have 122. How much spread is going to depend on how much spread is in the data and how much sample size we have. So let's say, for example, that sigma squared is equal to, just to make things simple, sigma squared is equal to 100, and that n is equal to 100. Okay, so that tells us that the variance of X bar around 122 is going to be 1. The standard deviation is also going to be 1, because the square root of 1 is 1. So that means if we saw 123, that's within the realm of possibility, certainly. If we saw 124, it's kind of like, yeah, what we're assuming is probably not correct. The true mean is probably not 122. If we saw 3 standard deviations away, 125, if that's what our sample mean was equal to, then it's like, yeah, okay, something's wrong here. We gotta just throw this down. And this is how we get our p-value. So we basically we assume the mean is equal to something. We can calculate the variance using the data, and then we can say how weird is what we saw. And what we look at is the probability we saw that value or anything more extreme. What is the probability we saw that or anything that's even bigger than that? So if we saw like 130, it's like, okay, yeah, okay. Clearly the mean is not equal to 122. Now it's not that simple because we don't know what sigma squared is, and we have to estimate it, and we estimate it using the data. And this takes us actually from a normal distribution to a t distribution. Okay, normal distribution to a t. The t is very similar to the normal. It just has a little bit wider tails, has a little bit more variation to it. There's also a very interesting story about how the t distribution was developed. It was developed by a guy who worked for Guinness. And he developed this, and it was like a trade secret of Guinness that it has this, he has this t distribution. God, I can't think of his name at the moment. Yanan would know. She can put it in the chat maybe. But he was so distraught about using it just for Guinness and not for publishing it like worldwide for everyone to know. So he published an anonymous paper about that, where he did the name on the paper was a student. So it's often called student's t distribution. But anyways, I'm getting out of here. Yeah, Gossett. Yes, thank you, Yanan. Thank you. How dare I forget? How dare I forget his name? So, but anyways, so this is the sort of thought behind hypothesis testing. We will use a t distribution. In R, we're going to use this t.test function. Okay, so let's go over to the HTML. See an example of this. So the average systolic blood pressure in the general U.S. adult population is 122 milligrams. Is the Framingham cohort different from this particular reference? So first thing we're going to do is we're going to look at the distribution of systolic blood pressure. We can see the average is that red line on the histogram. This data is not normally distributed, but we have a very large sample size here, 5,000 or so. So the central limit theorem is going to help us out here. So if we want to test the null hypothesis that the mean is equal to 122, we use this t.test. We are giving it the systolic blood pressures right here. This is going to do going to give us the t-test here. At the bottom, we can see what the mean systolic blood pressure actually was. It was 132, so quite a bit different than 122. And the p-value is, all it tells us is that it's less than 2.2 times 10 to the negative 16th power. So that is a number with like 16 zeros and then a 2.2. Obviously, the mean is not equal to 122 in this particular sample. So our original assumption that the mean was equal to 122 is incorrect. And when we do a hypothesis test, we reject the null hypothesis. There's a little bit of a technical thing. We never say that we accept the alternative. We say that we reject the null hypothesis. The other side of this is developing confidence intervals. This is similar to the hypothesis test, but it kind of does an opposite form of it. What we do is we try to give a plausible range of values for the true proportion given the data that we see. So you see the formula for it right here. We have X bar, then we add and subtract. There's a critical value here, usually around 2 times the sample standard deviation divided by the square root of n. The t.test function gives us this 95% confidence interval as part of the output. So we can see there that it's 31.69 to 131.7, let's say, to 133. We're 95% confident that the true mean is within that particular value. So what's the interpretation of this confidence interval? It says that if we repeated this study 100 times, the confidence interval that we make would contain the true mean 95% of the time. It does not say that the probability that the true mean is in this particular interval is 95%. It's not the same thing. So the correct interpretation says that if we did this study 100 times, about 95 of them would contain the true mean. So if we repeated this study, let's say this is our confidence interval that we found, if we repeated this study 100 different times and we got 100 different confidence intervals, about 95% of those confidence intervals would contain the true value. Let's say the true value is this right here. So most of the time it's going to be in the interval that we get, but not all the time. A wider confidence interval, more uncertainty. Narrow confidence interval, more precision. Here we have a very narrow confidence interval. Okay, this is a very narrow confidence interval. 131.7 to 133.0. That's because we have a very large sample size. Okay, you see the interpretation. All these interpretations have the wrong data in there, and I apologize about that. I made some mistake. But the mean systolic blood pressure in the Framingham cohort, it was actually 132.4. That's actually what it says. 95% confidence interval was 131.7 to 133.0. Significantly higher than the US reference value of 122. Highly significant. P-value tells us that. So we have hypothesis tests, we have confidence intervals. Okay? Hypothesis tests are used to test hypothesis that you have. Here we're interested in testing if the mean was equal to 122. Confidence intervals gives us some idea of where the true value is. Statistical significance versus practical significance. So the p-value is used for statistical significance. For example, here we found a very low p-value, which says we can be very sure that the true mean is not 122. Practical significance tells you whether the effect is large enough to matter scientifically or clinically. Well, we have a large enough sample, we're going to get statistical significance, but we may not get practical significance. For example, let's say we have a new drug and it lowers blood pressure by half a point in a study of 100,000 patients. This would be statistically significant. We have 100,000 patients, we can see that half point difference. Is that clinically significant? No. All right, half a point really doesn't mean that much. So practical significance is not necessarily statistical significance and vice versa. That's why we always like to report confidence intervals and effect sizes, not just p-values. So if you just report the p-value in this situation, people say, oh gosh, this is the greatest drug ever. Look at the p-value, it's very low, it lowered blood pressure. You have to have the confidence interval to actually give an indication for what this medication is doing. So we never want to just report p-values, we always want to have a confidence interval with it. Because that is going to give us information about what's actually happening. Some other tests that we can do. We've seen t-test, t-dot test. That's what we use when we have one group versus, and we want to test it versus a value. That's called a one sample t-test. We'll talk about two sample t-tests. This is when we have two groups and we want to compare them to one another. We'll also have paired two sample t-tests. So those are the main three tests we'll do for continuous data. We also have the Wilcoxon rank sum. We can use that for continuous data. When we have count data, like binomial data or categorical, so 0, 1 or 1, 2, 3, then we'll talk about chi-square tests that we can use to test if the associations are different between categorical outcomes. So how did that one sample t-test we just did, how does that work? What's the math of it? And when do we want to use it? Well, we want to use it in situations when we want to test, is the group mean different than some value? For example, a standard healthy fasting glucose is 90 milligrams per deciliter. You measure glucose in 25 lab mice after a dietary intervention. Is their mean glucose different than 90? So the null hypothesis, true means equal to 90. Alternative can be two-sided, that the mean is not equal to 90. Can be one-sided, where we say, all right, mean is greater than 90. Can be the other way, mean is less than 90. All we need here is a continuous measurement and a large enough sample size such that the central limit theorem applies. There's not many assumptions here on the data. It's really nice. Now you can see the test statistic. It's very similar to that z-score we went over earlier. Basically, how many standard errors is the sample mean away from the null mean? And this is going to follow a t-distribution. Usually, if this test statistic is greater than 2, it's going to give a p-value less than 0.05, which is commonly what we use for saying something actually happened. Okay, we went over this. I think I can skip that. All right, two-sample t-test. Two-sample t-test is one of probably the most used procedure in public health and otherwise. Situation here is we have two groups. We want to test if the mean is different between those two groups. We have a continuous outcome. We have a large enough sample size such that the central limit theorem is okay. Really not many assumptions here. For example, we measure gene expression in tumor tissue from patients who respond to treatment versus those who did not. Is the mean expression different between the two groups? The null hypothesis is that the two means are equal. So that's what we assume. We get the data, and then we see after we have the data, is this data so weird that we have to say, all right, that first assumption was not correct. That's when we get our p-value. Groups must be independent, so they're different subjects, for example. We'll talk about when they are the same subjects when we go over the paired t-test. The formula for the two-sample t-test, very similar to the one sample. We take the difference between the means. We divide that by the standard error of the difference. How we get the standard error of the difference depends on if we assume the variances are equal between the two groups. By default, we don't assume they're equal, but we can assume they're equal by using, in R, by using var equals true. Okay, let's just go to the slides here to take a look at this. So two-sample t-test. Do male and female participants have different mean systolic blood pressures? First thing we want to look is we want to look at the data here. Okay, we have females on the left, males on the right. They look pretty similar between one another. First thing I'm going to look at is the group level summaries. So the mean for females is 133. The mean for males is 131. The standard deviations are 24 and 19, relatively similar to one another. And this is how I am going to implement the two-sample t-test. So I use t.test and then sys-BP, that's my systolic blood pressure variable, tilde male. And that tells the t-test I want to test whether sys-BP is the same by the two levels of the male variable that we have. And what we get is a p-value right here, 0.016. We also get a confidence interval for the difference. This p-value, 0.016, says that, well, if they are actually equal, the data were really, really weird. So what we would usually say, we would conclude that the assumption that the two are equal was not correct. It appears that there's some difference between the systolic blood pressures in males and females. The difference is less than 2. I think it's 1.6 about the difference between the two. This is the confidence interval for the difference. So statistically significant here, there does appear to be a difference, but practically it's not a huge amount. 1.6 units is relatively small. So when we're testing, we want to give both of those. We want to give the p-value, whether they're different, and we want to give the confidence interval as well. So we can go to R. I'm going to go down to this part in the lab. You can always click this outline button, which will give you all the sections. I'm going to go to the 2-sample t-test section. I'm going to hit this down arrow right here, which is going to run everything above. I clearly don't have to run everything, but that's okay. Here we have, oops, I did it twice just to be sure. Here we have the box plots by sex, means, and standard deviations. So how I'm doing that, again, just how we're doing it day 2. Framingham, going to group by male, summarize, and mean blood pressure, mean standard deviation, looking at those, and then doing the t-test, implementing that t-test right down here. Okay, so I would like you on your own in the next 3 or 4 minutes or so. I'm going to copy this, paste it down here. Let's do the same thing, still use male. And this time, let's look at total cholesterol. So is there a difference between those two? Did something wrong there. First, do a histogram, then calculate the means and standard deviations, and then finally, we'll do a hypothesis test. Good. 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 Okay, good. Okay. So yeah, I mean the code is very similar, just swapping out cholesterol for swapping out systolic blood pressure for cholesterol. Here's the histograms between the two. Here's the statistics. The mean cholesterol for females, 239, for males, 233, corresponding standard deviations. T-test is highly significant, very low p-value, and we get a confidence interval between there. The average difference, is 6.3, with females having a higher mean cholesterol, 95% confidence interval, 3.7 about to 9.0. We can get all those statistics from there. And we have a little example of how you would interpret that. Next one, paired t-test. When to use this? This is when you have repeated measurements on the same subject. So for example, if we had systolic blood pressure before an intervention and after an intervention, and we want to say, is the systolic blood pressure before and after, are they different? Okay, is the values we got before, are they different from the values that we got after? If those two are different, that's an indication that the treatment was effective. Here we would use a paired t-test, something called a paired t-test. How does this work? Well, we take the difference, we get a new variable, di, which is the difference after minus before maybe, and then we test, are these differences, is that the mean of the difference is equal to 0? If it is, then there's no difference. If it's not, then there is a difference. We don't really have a good example here. We're going to do systolic and diastolic blood pressures. We don't have repeated measurements, so we can't test these things twice. So we're just going to test this for systolic and diastolic. Here we're calculating the pressure pulse, which is systolic minus diastolic. You can see it's clearly not equal to 0, nor should it be. Systolic is a lot higher than the diastolic is. But here's how we would do the paired t-test. Highly significant. Average differences, 49. It's another different way we can do it. We can give it the size systolic and diastolic and use paired equals true. We don't want to use unpaired when we have paired data. It throws away power. What about when we have categorical variables? So for example, is there an association between two categorical variables? And here we'll just focus on two binary variables. So is disease status associated with some exposure, where the exposure is yes, no? Or does a therapy treatment versus control group result in different proportions of responders or different portions of people getting the disease? Here, we summarize the data in a 2x2 contingency table like we see right here. So here, for example, we have 200 patients. They were randomized to drug and placebo. The outcome is just some response, yes, no, disease, or something bad happened to them, so on and so forth. So we had 100 people on the drug. We have 100 people on the placebo. Overall, 90 of the 200 had the condition. They had response equals yes. If the drug didn't matter, how many of those 90 would come from the drug group? How many of those 90 would come from the control group? So we have 100 in the drug group. We have 100 in the control group, even amounts. 90 of the 200 had the response. If the drug didn't matter, how many would come from the control group? How many would come from the treatment group? What's that? So you're writing that it'd be the same, but it would just add up to 90. Right. So it'd be 45 each. So if the drug didn't matter, we'd think 45 of those came from the drug group, 45 of those came from the placebo group. Because if the drug doesn't matter, there's no difference in the probability. So what we would expect, if there's no relationship between these variables, there's no relationship, we would expect 45 here, and we would expect 45 here. We don't see that. We see 55 in the drug group, we see 35 in the placebo group. Okay? Now again, it's kind of like the binomial thing. We're going to expect some differences. We don't think it'd be exactly on 45. Is 55 and 35, is that split? Is that weird enough for us to say there's actually a difference there? There's actually some relationship between these two variables. If there was a very strong relationship, we could see 60 and 30. Those 60 and 30 say, yeah, there's definitely, the drug's doing something. I don't know if response here is good or bad, but it's doing something. So we're going to do a hypothesis test for two variables. It's all going to be based on this contingency table that we see right here. Are the observed counts close enough to the expected counts? And the expected counts assume there's no association. So we have it right here. So if the drug and response were independent, we would expect 45 people to respond for each of these groups. This is used to create something called a chi-squared statistic, where we look at the observed minus expected squared over the expected. We sum that over all cells in our 2x2 table. We can run this in R. To run this in R, we have to first get the table, and then we give that table to the chi-squared.test function. Let's take a look at how this works. What we're going to look at is smoking and hypertension. Is there an association between these two variables? We get our table first. So we say table, smoker equals, give it the smoker variable, hypertension equals, give it the hypertension variable. This gives us our 2x2 table. We could change these two proportions, like we see right here. Here we're getting row proportions. So among the non-smokers, 64% have hypertension no, 35% have hypertension yes. Among the smokers, 74% have hypertension no, 26% have hypertension yes. Okay, let's look at the, we can plot these here. The smoker versus non-smoker. Yeah, why I'm pausing here is because looks like smoking is healthy here. Who knew? So I was like, what, is that right? Yeah. Yeah. There are some, okay, I'll tell you a story about this. So we do this chi-square test, chi-squared.test of the table. We find it's highly significant. That tells us, okay, the assumption that these two variables were not associated, it was not correct. The two variables appear to be correct. When we do this, we always want to look at the expected number of counts and make sure that they're all greater than 5. Interesting thing about this. This just tells us whether the two variables are associated with one another. It doesn't tell us why the two variables are associated with one another. For example, if you look at babies that are underweight, okay, babies that are born small, those that are born small from mothers who smoked during pregnancy have better survival rates than those who are born small from mothers who did not smoke during pregnancy. Doesn't make sense, does it? Well, the problem is that mothers who smoke, their kids are more likely to be born small. Okay? So mothers who don't smoke, the kids that were born small, it's a bigger warning sign that they were born small. If they were born small from mothers who smoke, yeah, that kind of happens all the time. The kid's usually okay. Doesn't mean you should smoke because being born small is not a good thing to begin with. But so again, we can see associations between variables, but it doesn't mean the relationship between those two is exactly how we think it is, and probably something is going on like that here. I really didn't look through this though. I was surprised when I first looked at this. Another chi-squared test is, so when we have small cell counts, we can use something called the Fisher's exact test. We see an example of that here with stroke and diabetes, where we have some very small cell sizes, and we can see the expected counts are less than 5 in some situations. And here's the code for that, Fisher's exact test. The last one, and I'm just going to go over this one briefly, is the Wilcoxon rank sum test. So the t-test is very useful, but it relies on the central limit theorem. So you have to have either normal data or you have to have a big enough sample size. Sometimes you don't have that. Sometimes you have very skewed data and a small sample size. When you have that, this is where the Wilcoxon rank sum comes into play. This doesn't assume normality. How it does that is it just uses the ranks of the data. And it takes the data, lists them all, it ranks them, and it says, well, if these data come from the same distribution, the ranks should kind of bounce around from one group to the other. So it doesn't rely on the actual data values at all. It just relies on the rank of them. But it's a useful test to use when you have other situations. Here we have an example of it for glucose, which is a pretty highly skewed distribution that we can see here between diabetics and non-diabetics. Now here we have a big enough sample size so we could do a t-test, but here we are using a Wilcoxon rank sum test. So this is one, it's an alternative to the t-test that we can use when we have data that are highly skewed and our sample size maybe is not as small. So to summarize all these tests that we have, all very useful. We have continuous data, one sample, testing it versus a reference, one sample t-test. Continuous data, 2 independent groups, males, females, for example, 2 sample t-test. We have paired data, systolic blood pressure before or after, for example. That's when we can use the paired t-test. When we talk about categorical data, testing for associations there, that's when we use the chi-square test. We have small samples, the Fisher exact, and then the Wilcoxon rank sum is one we use when we have non-normal data. When we use a t-test, first thing we do want to look at is a histogram. Okay, just are the data relatively normal? Going to make us feel a little better. When we're using a chi-squared, remember, check that all the expected cell counts are greater than 5. The code to that is in the HTML file. For Wilcoxon, we don't have to look at a histogram, just we need to make sure that the data are independent. So one subject is not impacting another subject, one another. Common misconception, you should not choose your test after looking at whether the result is significant. That inflates your false positive rate. So decide on your test based on the data and before you run the analysis. We're going to work on this stuff in the afternoon. We have some questions in the lab. They're going to be revolved around probability, the distributions that we talked about, binomial, Poisson, those are going to be counts, normal distribution, central limit theorem. Remember that says that the sample mean is going to be approximately normally distributed if we have a large enough sample size. A p-value. This measures the evidence against the null. The p-value is very, very small. That says that assumption that we made in our hypothesis is incorrect. For example, if we assume that the mean Systolic blood pressure is 122. How weird is the data that we saw? That is going to get the p-value, that's what that measures. Confidence interval says, based on the data we have, what is a plausible range for the true value of the parameter? That could be the sample mean or the sample proportions. Confidence intervals are important because statistical significance is not necessarily practical significance. If we have a blood pressure medicine, okay, we could do a test on 100,000 people and say, oh, it's statistically significant. But how much is it actually changing the blood pressure? Oh, a real life example of this. Tamiflu. Have you ever used Tamiflu before? What do you use Tamiflu for? No? What's Tamiflu?
Fever, flu.
Yeah. Yeah. When you get the flu, this is basically the only drug that they have is Tamiflu. Okay, which shortens the healing time. You know how much it shortens the healing time by? On average, a half day. You get healthy a half day faster. That's right. We spend millions, maybe even billions of dollars on a drug that on average gets us healthy a half day quicker than if we didn't use it. Okay? Statistical significance is not always practical. I got a whole bunch of horror stories. You don't want to hang around with me. Okay, so that's it for the morning. Come back in the afternoon. If you want to start on the lab, go ahead. I don't think we're going to do all the questions. I'll post on the Slack channel what questions we are going to focus on here today. But I will be back on the Zoom in the class at 1 to work on those and help you guys out with those. All right, I will see you guys in a little bit. Have a good lunch. So for this afternoon, we're going to do some work in R, doing the things that we did in the morning section. There's going to be 3 questions that we are going to focus on. Of course, we're going to you can complete all of them. But exercise 1 is going to be a 1 sample t-test, again with the Framingham data, using a little different, using a different variable, asking for some figures, a hypothesis test, and an interpretation of that. Then question 4 is going to look at some categorical variables, and doing some getting some tables, some 2x2 tables, chi-squared tests, some plots, and then an interpretation of that. And then exercise 5 is where you will choose the right test yourself. So I'll give you a little quick question, and you will do the, hey, which test is going to be correct, and then implement it. Okay, good. All right, so this is going to be as normal. So you do a Quarto document yourself, similar to what we've done before. This is just using the Framingham data. So no additional data that you'll have to do. I'll be up here. We'll also have people online if you have any questions.